Black holes are famous for being absolute cosmic traps where nothing escapes. They are completely silent, invisible voids. But when two of them collide, they create the most violently explosive, high-energy events in the universe. As they smash together, these massive objects violently churn the very fabric of spacetime, sending out massive ripples known as gravitational waves. Knowing a crash happened is one thing. The real mystery for physicists is what occurs in the exact fractions of a second after the impact, as the mangled, chaotic spacetime struggles to settle back down into a perfectly smooth spherical shape. Because we cannot see a black hole, we have to deduce its physical properties by listening to the exact shockwaves it leaves behind in its wake. On January 14, 2025, massive terrestrial detectors like this one recorded a colossal disturbance named GW250114. What made this specific signal so valuable was its sheer volume. It had a higher signal-to-noise ratio, meaning it was roughly 3 times louder and clearer than the very first gravitational wave discovered in 2015. That extreme clarity allowed the signal to easily punch through the detector's everyday background static, handing scientists pristine, highly detailed data of that final post-merger settling phase. With the static cleared away, physicists could finally isolate the specific, distinct acoustic tones of a newly born black hole. The scientific term for this crucial window just after the merger is the ringdown phase. It is the exact period when the newly formed black hole is calming down into a stable state. Just as a struck bell vibrates at a set of specific acoustic frequencies, the agitated black hole vibrates the surrounding spacetime in a set of distinct, fading tones. Physicists refer to these characteristic spacetime vibrations as quasi-normal modes. In the span of mere milliseconds, the chaotic energy of the collision organizes itself into a structured, highly predictable chord of gravitational waves. Black hole spectroscopy dissects the GW250114 signal into individual acoustic parts. The dominant vibration is the fundamental tone. Layered above is the first overtone, a faster fading, higher-pitched vibration lasting just 3 milliseconds. Finally, the secondary tone oscillates at twice the fundamental frequency. Much like isolating a bass guitar or a snare drum from a complex audio track, separating these distinct quasi-normal modes allow scientists to independently measure the physical properties of the black hole. The no-hair theorem states that an astrophysical black hole is completely defined by only 2 relevant quantities, its mass and its spin. Because of this rule, the exact frequencies and half-lives of every single ringdown tone are mathematically locked to those 2 specific numbers. If we calculate its mass and spin, we know exactly what it should sound like. The ringdown tones serve as a strict mathematical fingerprint. If the detected tones in the actual signal do not perfectly match the predicted fingerprint, it means our current understanding of gravity is broken. The analysis of GW250114 acts as an ultimate stress test for Albert Einstein's theory of general relativity. Researchers used the signal to check if the remnant behaves exactly like a mathematically perfect rotating Kerr black hole. This contour plot shows the results. The black markers represent the expected theoretical values for the black hole's tones based on general relativity, and they land perfectly within the red, green, and yellow-colored regions, mapping the actual measured data. For a final verification step, the researchers mathematically subtracted the best possible theoretical relativity waveform from the raw data. They found absolutely nothing left behind, except ordinary detector noise. Einstein's century-old theory of general relativity survives intact. It accurately predicts the mechanics of the most intense, rapidly changing gravitational fields known to science. The unprecedented clarity of GW250114 systematically ruled out alternative theories of gravity, leaving Einstein's predictions as the definitive model for the extreme universe. This chart displays those limits. Measurements from this single event, shown as blue stars, place upper bounds on deviations from general relativity that are 2 to 3 times more stringent than combined past data from dozens of signals, marked by red squares. As gravitational wave detectors become even more sensitive in the coming decades, they will capture even louder signals, enabling deeper, far more precise spectroscopy. Analyzing the harmonic ringing of these mergers allows us to push the fundamental laws of physics to their absolute limits.